Welcome back, grade 10s. In this lesson, we are going to continue with the section of revision of matter and classification. So we got up to pure substances and mixtures. So materials may be a pure substance or a mixture, meaning a mixture of different pure substances. So let's define a pure substance and remember that definitions need to be learnt word for word. A pure substance is defined as a substance that cannot be separated into simpler components by physical means. And in grade 7, you would have learnt about the different physical means of separation, and we're going to recap it shortly in this lesson. Now, in real life, very few materials occur in a pure form. Most things in real life are actually found as mixtures of pure substances, meaning that there are different pure substances that exist together in one space. So a mixture is defined as two or more pure substances existing together, meaning that they can be separated into simpler components by physical means. So whether or not you're able to separate your substance by physical means will tell you whether it is a pure substance or a mixture. So over here, we've got a piece of coal, which is made up of a whole bunch of simply coal atoms. So that would be a pure substance. It is only made up of one type of material, and carbon atoms cannot be separated into simpler components at all. Now over here, we have distilled water. Distilled water means pure water. So generally in our tap water, there will be some salts, some chlorine. So tap water is not pure water, but distilled water is pure water, pure H2O. Now here we can see that all we have in our container is one type of molecule or one type of compound, H2O. Now, where students often get mixed up is they think that this would be a mixture because each water molecule is made up of one oxygen and two hydrogen atoms. However, those have been chemically bonded. So once a chemical bond has formed, you now have a new substance with its own set of properties. So this distilled water is pure H2O, and this pure H2O is, in fact, a pure substance. This over here is not a mixture because this is made up of chemical bonds, meaning that it forms its own pure substance. And if there's only H2O in the container, then it's a pure substance. And again, a pure substance cannot be separated into simpler components by physical means. So there is no way of separating the oxygen and the hydrogens from each other by physical means, only by chemical means. Now, if we look at this diagram over here, well, we've got pieces of carbon inside water. Now, the carbon and the water, they don't chemically react. They don't form anything new. They just coexist in the same space, and that's what a mixture is. It's two or more pure substances that exist together. So that means that they can be separated by physical means. And if we wanted to separate the carbon from the water, we would simply have to use our hands to remove the carbon. So let's now recap the different means of physical separation. So the simplest one is hand sorting, which is what I mentioned in the previous slide. But hand sorting is generally used for separation of solids that are distinct from each other. They look different from each other. And a big disadvantage of hand sorting, you would have learned in grade 7, is that it is a very time-consuming process. Sieving is used to separate solids that have different sizes. So, for example, separating gravel from sand. Gravel is bigger pieces than sand. So the smaller pieces, the sand, will move through the sieve and the gravel will be left behind. Now, filtration is used to separate a non-soluble solid or an insoluble solid from a liquid. Insoluble means that it doesn't dissolve. So sand doesn't dissolve in water. So we take our mixture of water and sand, we take a funnel and we line it with filter paper. Now, the filter paper has got teeny tiny holes that allow the water to move through, but it leaves the sand behind. The substance that moves through the filter paper is called the filtrate, and the substance that remains behind on the filter paper is called the residue. Now, why can't we use filtration to separate a soluble solid from a liquid? So, for example, salt is soluble in water. So if I took a mixture of salt and water here, and I placed it on the filter paper, why would filtration not work? Well, it's because the salt dissolves into the water, and the salt would move through the filter paper right along with the water. So this is why filtration only works for non-soluble or insoluble solids inside a liquid. It does not work for solids that are soluble inside a liquid. Magnetism is used to separate a magnetic material from a non-magnetic material using a magnet. Now, evaporation is a process that we use to separate a soluble solid, meaning, for example, a mixture of salt and water. So now the salt is soluble in the water. The salt dissolves in the water. Now, the soluble solid, being the salt, is known as the solute. The salt-water mixture is called the solution. And the water, which is the substance that the soluble solid is dissolved in, is known as the solvent. Those are very important words to know the meanings of. So let's take a look. Here we have our salt, which is our solid. Now, this is going to be the solute because it is soluble in water. The water is the solvent. Once we have a salt-water mixture, together, the solute and the solvent together form a solution. Now we take the solution of water and salt, we heat the solution to the boiling point of water. The boiling point of salt is much higher, which means that the salt pieces will remain behind, while the water would have evaporated into the atmosphere. But what happens if we have a solution, meaning a mixture of a solute and a solvent, but we don't want to lose the solvent, meaning we don't want to lose the water to the atmosphere? So distillation is also used to separate a soluble solid from a solution, so to separate salt and water from each other. Now on the left, we have the flask containing the solution, and the solution in here is the salt water. The water is known as the solvent, and we want to heat up the solvent to its boiling point. Remember that salt has got a much higher boiling point. So at 100 degrees, the water will boil. Now, here we have a thermometer just to track the temperature, and this over here is called a condenser. So as the water boils and turns to gas, well, it moves up here and it's got nowhere to go, so it's forced down the condenser. And the moment it gets in here, it cools down, and it turns into tiny little droplets of water, which then slide down into the beaker on the right. So when this process is finished, what we end up with is the salt in the flask on the left and the water in the beaker on the right. So that allows us to separate a soluble solid from a solution, and we end up not losing the solute or the solvent. Two important things to note here. Well, this over here is just cold water surrounding this condenser just to speed up the condensation process. And the substance that's left on the right-hand side inside the beaker is known as the distillate. Now, what we need to understand also is that this process is not only used to separate a soluble solid from a solution, we can also use it to separate out different liquids that have different boiling points. So the crude oil would be placed here. This mixture would be heated up to 150 degrees Celsius, which would then allow the petrol to end up as the distillate on the right-hand side. Then we have to remove this beaker, place a new beaker, boil this mixture to 200 degrees Celsius in order to separate out the kerosene. Then we end up with kerosene as a distillate over here. From there, we remove this beaker, put a new beaker in place, and now we still have to separate the diesel from the fuel oil. So we're going to boil this mixture over here to 300 degrees Celsius. That means that the diesel would end up as the distillate on this side, and the fuel oil will be left behind. Now, the last means of physical separation that we're going to learn about is called chromatography. And we haven't learned about chromatography before. Chromatography is used to test the purity of dyes like paints, foods, beverages, even medicines. It's used in the sports industry to identify potential drugs in the bloodstreams or the urine of athletes. Now, how does paper chromatography work? Well, paper chromatography is able to separate substances into their individual components. And if a substance is pure, then we will see on the paper chromatography that there is only one component at the end of the process, meaning a pure substance, versus several components at the end of the process, meaning a mixture. So let me explain that a little bit more clearly. So this over here is chromatography paper. Now, chromatography paper is made of normal filter paper that we often use in a lab. If you are taking life sciences, you might have learned about capillary action. Capillary action takes place in the xylem of plants, and that is how water gets from the root of the plant to the top of the plant. Water is kind of a sticky substance, and we'll learn more about that in grade 11. But what we need to understand here is that by dipping chromatography paper, which is just filter paper, into a little bit of water, well, that water will just rise through the chromatography paper, and that's due to capillarity. Now, as the water moves up the chromatography paper, well, it pulls, in this case, it's different dyes, it's different colors, it's red and green and blue and black. So it gets pulled up. Now, if, for example, this blue dye is made up of purple and light blue, well, at the end of the process, well, we'll see more than one color. The water has separated this original color into the dyes, the different colors that it is made of. And the reason that it does that is because different dyes and different substances have different masses and different densities, which is why each one will end up at a different spot on the chromatography paper. So this is a real life example, and to me it looks like the red is a pure substance, but the other three are not pure substances. They are made up of mixtures of different dyes, of different colors. Now, imagine here we took a black pigment and it has separated into red, yellow, and blue. Obviously, when we have a diagram, it looks a lot neater and it's a lot easier to analyze. But here we can definitely say, well, the black color that we used here originally is actually made up of red pigment, yellow pigment, and blue pigment. But now, if we take pure red, pure blue, and pure yellow, we place those colors here, well, the red will pull up to one point, the blue, which has different characteristics and different density, will pull up to another point, and the yellow will pull up to a different point to the other two. So these would be our reference materials. So we know that pure red reaches here, pure blue reaches here, and pure yellow reaches here. And then based on that, we can compare our original mixture. Now you can imagine that, for example, testing a urine sample in the sports industry. Well, we would have a whole bunch of illegal products that should not be in an athlete's urine or in an athlete's bloodstream. We have the standard reference for where those products reach along the chromatography paper. And from that, by separating out the different components in the urine, we can see if any of the substances in the urine would match up to an illegal drug. Let's consider the paper chromatography process for ink C, D, and E. And what this shows us is that ink E is a pure substance because it is only made up of one type of pigment, whereas inks C and D are each made up of mixtures of pigments. So to clarify the paper chromatography process, you should watch this video. Now, a pure substance will be made up of one type of atom or element or molecule or compound. So, for example, a copper bracelet that is made up of only the element copper is a pure substance. But a glass of distilled water, which is made up of H2O molecules, which are chemically bonded, is still a pure substance because once chemical bonds have formed, then you get the creation of a new substance with its own set of properties. So again, once a chemical bond has formed between atoms, a new pure substance forms with its own unique set of properties, which is why in the case of pure distilled water, well, this is a pure substance. So let's consider the following. Carbon is a black solid, and it is made up of the element carbon only. It is a pure substance. Oxygen is also a pure substance because it is made up of only O2 molecules. It's oxygen gas. It is a pure substance. Now, here we have a mixture of carbon and oxygen, meaning that carbon and oxygen exist in the same space, but there's no chemical reaction that takes place between them. So the carbon maintains its own unique set of properties, and the oxygen maintains its own unique set of properties. Now, once a chemical reaction has taken place between carbon and oxygen, well, then carbon dioxide forms. Carbon dioxide is a gas, it is a greenhouse gas, and it has its own unique set of properties that are different to the properties of carbon on its own and different to the properties of oxygen on its own. So here we have a mixture, and we can separate out the carbon and the oxygen by physical means, but here we have a pure substance. We cannot separate the carbon dioxide by physical means. If we wanted to separate it, we would have to use chemical means. Can the carbon or the oxygen or the carbon dioxide be separated by physical means? And the answer is no. We cannot break down an atom like carbon, and we cannot break down the bonds in O2 and in CO2 by physical means. Can the mixture of carbon and oxygen be separated by physical means? Well, the answer here is yes. Mixtures can be separated by physical means. They're not chemically bonded. Now, because each pure substance has its own unique set of properties, we may use those properties to test for the purity of a particular substance. So, for example, we know that pure water boils at exactly 100 degrees Celsius, and pure water solidifies at exactly 0 degrees Celsius. Now, given a glass of tap water, would we expect it to boil at exactly 100 degrees Celsius and to solidify at exactly 0 degrees Celsius? Well, the answer here is no, because tap water is not pure water. There are other substances inside that water. There's salts like calcium and magnesium, which means that tap water will not display the properties of pure water. As mentioned above, in nature, most materials are found as mixtures. So here are some examples of mixtures in nature. The air around us is a mixture of gases, mainly nitrogen and oxygen, as well as some other gases like carbon dioxide. A fruit is a mixture of sugar and water and fiber and vitamins. Soil is a mixture of sand and pebbles and plant matter and animal matter. Alloy. This word's already been discussed. It is a mixture of metals or a mixture of metals with non-metals. But if it's mixed in with non-metals, the resulting material has to have metallic properties to be considered an alloy. So steel is always a mixture of iron and carbon. So it is a mixture of a metal and a non-metal, but the resulting material, steel, has metallic properties. Depending on the properties that we want for that steel, we might add some other metals to the steel. Another example of an alloy would be if you win a bronze medal. Well, what is bronze made of? Bronze is an alloy of copper and tin. Very importantly is that in a mixture, the substances that make up the mixture, remember that they keep their physical properties. So if we mix sand and water, sand still has the properties of sand and water still has the properties of water. They just exist together in the same space. And the other very important thing to note is that a mixture doesn't have a fixed ratio. Remember that we said that any compound or molecule has a fixed ratio of the elements that make it up. So any H2O molecule is made up of 2 hydrogen atoms and 1 oxygen atom. That's a fixed ratio. However, when it comes to mixtures, you can make a mixture of sugar water with 1 cup of water and 1 spoon of sugar, or with half a cup of water and 3 spoons of sugar. Either way, it is a mixture of sugar and water. And lastly, when it comes to mixtures, we need to be able to differentiate between homogeneous and heterogeneous mixtures. A homogeneous mixture is simply defined as a uniform mixture, and that means that it looks the same throughout. we cannot see the different components. So for example, here we have a cup of coffee that is made up of water, coffee powder, maybe sugar, but we cannot see the different components of the mixture. It looks the same throughout. Tap water is another example of a homogeneous mixture, as is the air around us, as is steel. A heterogeneous mixture, on the other hand, is a non-uniform mixture. It does not look the same throughout. You can see the different components of the mixture. So here we have a bowl of cereal with milk. Chocolate chip cookies would be another example of a heterogeneous mixture. A soil sample would be another example, as well as a carbonated drink, which contains the liquid with carbon dioxide bubbles in it. If you had to have a flat drink where all those carbon dioxide bubbles have already escaped into the atmosphere, well, that would then fall under a homogeneous mixture. This is a very useful video on pure substances versus mixtures.